initially defined that how to compute and what is the meaning of integrating a vector field over an arbitrary curve. And then we talked about a very special kind of vector field that is the gradient vector field activity. And a vector field F is a gradient vector field that you defined it last time. That if you can find a smooth scalar field whose gradient is F. Okay? So phi is a smooth scalar field where R is some open set and its gradient is basically F. Okay? So F would be a gradient vector field if you can find such a scalar field whose, if you compute gradient, you get F. And this phi has a special name, so we call it it's the potential. Okay. Potential of scalar field, potential of vector field, potential field. Okay. And then we proved finally a second fundamental theorem of line integrals, which says that if you have a gradient field, so in other words, you have F that is a gradient of the phi, okay, and then under certain hypothesis, okay, and you have, say for example, a curve that lies in the domain of the scalar field, or this scalar field phi, okay, and this curve is like this domain U, and in that domain you have this curve actually C, which starts from a point A and ends at some point what we call B, or we called it A star and B star in our last discussion. Yes. Okay, and then if you compute the the line integral of such a vector field along the curve C, then this would be same as that you simply evaluate the phi at B star minus the phi at A star. Okay. It's really analog to what you call in one dimension you did roughly fundamental theorem of calculus. It's really analog to it. Okay, so this is something that we proved in our last discussion. So what I would like to do, I would like to demonstrate this basically through an example. Okay. So consider a vector field F, okay, that looks like say 2x, y, z, okay, and x squared v and x squared y. Okay, so I'm quickly go through it. And consider a curve that is parameterized by a parametric representation, that is p squared and pq, where the p is sitting between 1 and the 2. Okay. So what I would like to do, roughly, I would like to verify this result, that if you're going to compute, for example, the integral of f directly, okay, along the curve C, by definition, this would be same as that if you can find such a potential first phi and then evaluate it onto the endpoint of the curve, actually, then you should have the same result. Okay. I'm not computing this integral f. Okay, because I know I can, compute it, so I'm just directly writing it that, if you want to compute this integral, we need to do what? We need to evaluate f at the p of t and take its dot product with p prime of t and integrate everything from a to b at d. So you can easily compute it actually. Okay, so we did it last time, how to compute such kind of numbers. So this is going to turn out to be 127.
So यहाँ पे जो end points होंगे कर्व की,
वो p of 1 और so the a star is going to be what? So it's going to be 1, 1, 1.
Yes, yes.
And B star is going to be, that you substitute
2, 4 and 8.
2, 4 and 8. So this is going to be A star and B star. Okay? Obviously, if you, the first thing would be if you want to compute the other side, you need to know the potential actually. Okay? So in other words, you want to basically solve this equation for the phi. So F is known to you, so the phi is something that is unknown actually. Okay, we will later basically address a theorem actually that is going to guarantee us that whether such a phi always exists or not. In this case it exists actually, so we are assuming that this phi exists, so we like to find that phi. Okay, and later we will see that there are fields for which you can't find such phi actually always necessarily. Okay. So what is F? So F is like this, this 2x, y, and z, and x square z, and x square y. And the gradient of phi is what? So it's partial phi by partial x, okay, and partial phi by partial y, and partial phi by partial z. Okay? We're going to compare them where phi is unknown. We're going to have partial phi by partial x is same as 2x by z, partial phi by partial y as x square z, and partial phi by partial z as x square y. We might give them names of 1, 2, and 3. So this is nothing. This is just system of first order partial differential equations actually. First order partial differential equations. Okay. So I can begin with any equation. So let's begin with the first. So I like to find the phi actually. Okay. So what I need to do? Integrate both sides with respect to the x. Okay. So integrate both sides with respect to x. So when you're going to integrate both sides with respect to x, or this side with respect to x, what are you going to get? So so roughly you are partially integrating actually, because this is partial differentiation actually. Okay. So when you are partially integration, there is nothing like partial integration, but just formally speaking, you can say that it's a partially integrating with respect to the x, and you are assuming y and z as constant actually. Okay. So what you're going to get? You're going to get 2 times of x square by 2 and yz plus a constant. Okay, but you're not going to have a constant actually. You're going to have a function actually. Why? Because y and z are constant. So this constant, whatever the constant that you are saying, is going to depend on the y and z. So it's no more will be a constant. So I mean, if you are in one dimension, yes, it will be constant. So here it's going to be some function depending on y and z actually. Okay. So I have some form of the phi. Okay. So the phi of x by z is this x square y z plus this unknown bit actually. Okay, so I'm interested in finding this unknown bit. So let's call this equation number 4. So any clever strategy to find this unknown bit? So another thing that you can do is that you differentiate phi with respect to y and equate it with the second thing actually. Okay, so if I differentiate this with respect to the phi, so what you're going to get? Y. So you're going to get x squared z plus f of yz. But from equation number 2, I know that this is x squared z. Okay. So what does this mean? This means that but you need to also differentiate this with respect to the y, because differentiating everything with respect to y, you have to also differentiate it. So this means that partial f by partial y is going to be yz, and that's equal to 0. Right? So now how to find the f? Partially integrate roughly with respect to the y. So you're going to get f of yz. Okay, so the integral of 0 is going to be 0 plus a not a constant but a function. But that function is going to depend now on z only. Okay, so f yz is independent of the z. Okay. So what should I do next? In other words, I can now update my equation number 4 actually. because I know that f of yz is now g of z, so the updated equation number 4 is going to be phi of x y z x square yv plus g of z. So now you're going to final obvious step actually, that how to compute g of z is that you take this phi and differentiate with respect to the z. So you're going to get what? You're going to get x square plus the derivative of the g with respect to the z. Okay? But I know that this bit is x square y actually. I mean, if a vector field is really a gradient field, you will see that things are cancelling out. Okay, not necessarily always, but you will find that you will feel that they are coming in a good shape actually. So you're gonna say what? So you're gonna say partial g by partial y with partial g of z by partial z. But since f is a function of z, so you can even call it a total derivative actually. And this is equal to the 0. Okay. And what does this mean? So the g of z is purely a constant actually. Okay? Hence the updated version of the phi is what? So the phi of x, y, z is equal to this x square y v plus some constant. Okay, so this is the potential, and you can quickly verify it. I mean, if you differentiate it with respect to x, are you getting 2xyz? Differentiated with respect to x, 2xyz. Differentiated with respect to y, so you're getting x square z. Differentiated with respect to z, you're getting x square y actually. So everything is fine actually. So you can see that it really satisfies the equation. Okay, okay? So what is the final thing that I need to do? I need to compute the phi at these two and the points of the curve actually, okay? So, I can have phi of 2, 4, 8 minus phi of 1, 1 actually, okay? So this c will cancel out from the both, and you're going to get 1. So you can make calculations of 4, 16 and 8, you will see that it's going to be the 127. You can check it actually, that is really going to be the 127, okay? So what is the good thing about this example? So you really saw that it works. Okay, the formula works. This theorem works. I mean, if your field is a gradient field. And the second thing is you also learned that how to compute the potential, scalar potential actually. Okay. So physically, this potential is going to be really a potential energy. We'll get into that. Okay, we are happy with it? So let's move on. Let's move on to it. Let's do kind of now like these I mean, what are the immediate consequence of this second fundamental theorem of calculus actually? The second fundamental theorem of calculus tells you that if f is a gradient field, in other words, it's a gradient of a scalar field, then this integral does not depends onto the curve, it just depends on the endpoints actually. Okay, so in other words, if I'm sorry?
It's independent of what?
It's independent of the path, independent of the curve actually, okay? So so I know the gradient fields are such fields which are independent of the paths actually. But you can also have fields that are not necessarily gradient, but they are also independent of the path. So any such a field, so this kind of motivates us to define a new class of the fields. Okay, and later I'll make a picture of it. Finally, that what is what and so this defines, this allows us, this motivates us to define that, okay, there can be fields in which this integral is independent of the choice of the curve actually, or independent of the paths actually. Okay, we're going to say that a vector field is a conservative vector field. You might have heard this on, in your physics courses actually. Okay, so for example, gravitational field is a conservative vector field actually. Okay. So conservative field, conservative vector field. Okay. So it's a conservative for vector field is a conservative vector field if its line integral is independent of the path, actually independent of the curve that you choose. Actually, okay. That's what really the definition is. That. So you have a continuous vector field F. Okay. Obviously, it's defined on U to Rn, where U is also a subset of Rn. So a vector field is always a map from same dimension to the same dimension. Okay. R3 to R3, and R2 to R2, so such an interaction. So Rn can be the vector fields actually. So a continuous vector field F, okay, is conservative. Is conservative, okay, if no matter what point you take from the domain of the F, okay, and no matter what rectifiable curves you take, okay, all rectifiable curves C1 and C2, okay, from A to B, okay, we have this. This is F. If you compute the integral of F around C1, this is same as the integral of F around C2. So what does this definition say? So this is saying if this is the domain of the vector field, and you take 2 points of this vector field, and you join these 2 points through any rectifiable curve actually. So take this rectifiable curve and take this rectifiable curve actually. Okay? And you compute the integral along the both curves. You will see that no matter what path you take, their integrals are same actually. Getting the point? Their integrals are same. That's what essentially it says. That take 2 points A and B. Okay. Take 2 points A and B and join, and you for example, you compute the integral around this curve or any other curve. It doesn't matter. Okay. That joins A to B, and you compute the integral along that curve. The integral is going to have a unique value actually. Right. So therefore you say that this integral of this field is a conservative vector field, that it just depends on the points. It doesn't depend on the curves that join them actually. Okay. You can have an equivalent formulation of this definition. Okay. The equivalent formulation of this definition can be this. That, think about it. Okay. So if I, for example, get rid of all other paths, I can only just take 2 paths, this path and maybe other wiggly path, but you reach to the A to B. So if you see them together, this is like a loop actually. This is like a loop. Okay. So what do you think? What should be the value of the integral along this entire loop actually? If you have such a vector field actually, huh?
Must be 0.
Why it should be 0? Think about it. So if this is true for any curves C1 and C2, okay? So take C1 to be C and take C2 to be the reverse curve of the C actually. Okay? And compute the integral. So what would be the integral? So this integral is going to be C. And this integral is going to be the integral of F but over the reverse path. But I know the integral of this over the reverse path is same as the minus of the integral over the path actually. So you have the equality. So you have equality, that means that the integral is 0 over the closed loop actually, so where C is a closed loop actually. What of the physical interpretation of this integral is going to be that you can treat this as, think about it. So what is the definition of integral along the curve? See, I know that this definition is that okay, you consider the f at the point p of t and multiply it with the p prime of t and integrate it over a to b actually. Okay. Now imagine this p is a path of a particle. It's a trajectory of a particle actually. Then p prime of t is representing what? P prime of t is going to be displacement actually. And assume that F is force. Okay? Really the force actually. Gravitational force, for example. Okay, it's the force. So what is, so you are taking the dot product of the force with the displacement actually.
It's sort of work.
So it's a work actually. Okay, so it's a work. So this integral, for example, one of the physical interpretation of this integral of F along C, that this is the work done by this force actually. Okay? And so physically we can say a vector field is conservative if the work done along any 2 points, paths joining 2 points is same actually. The work done along a closed loop is always 0. Okay, so you might have heard something like similar.
We are treating rectified curves as a displacement.
Yes, P of t, yes, I'm denoting it by parameterization, I'm denoting it by displacement actually. Not the curves, but the movement, we are assuming that the particle is moving along the curve actually. Okay? Or maybe some object is moving along the curve, then P of t is going to represent, so P prime of t is going to represent kind of the displacement actually. Okay? Is it making sense? That could be one of the interpretation. Anyway, so let's get to the second fundamental theorem of curve. First fundamental theorem of line integrals, which is even more interesting actually. Okay, which even tells you a very interesting thing about the conservative vector fields actually, or maybe give you the relationship between conservative vector field and the gradient vector field. Okay, so in other words, at the moment I know that for gradient vector field, so you can ask a question, I know for gradient vector field, this work done or the line integral just depends on the endpoints of the curve actually. Okay, so it doesn't depend on what path you choose. So conservative vector field is also something similar. The question is, but they have different definition obviously. Okay, so you can obviously ask a question actually that okay, when a conservative field is gradient field actually, or you can say, is every gradient field is conservative vector field? Or conservative vector field is a gradient field actually. So what is the relationship between? So if I have a set of gradient vector fields and I have a set of conservative vector fields, so which set is bigger? Okay, so the first fundamental theorem of line integrals answer this question actually. Okay. Alright, but there are some definitions that we should do. Then maybe I'll state the theorem and do the boring part, but it's important that we should learn that why things are true, they are the way they are actually, so why they are the way they are. Okay. Alright, so has a very interesting definition. Okay, you will learn about this notion more in detail in your topology course. So it's called the Pathconnected. Okay, so you're going to say, if you have a region D, so imagine you have a region D, so I'm going to say that this region D is path connected. Okay, if I choose any 2 points between this region, then I can always find a curve that joins them. Okay? So take any 2 points, so take these 2 points, okay? You can always find a curve that joins them. Now that curve might be a straight line, and that curve should entirely must be contained in the region actually, shouldn't go outside the region. That's what another important thing is there. Okay? So that might be a line. Okay, you take any other 2 points. Okay. Take 2 points and you can find a curve that joins them. So you're going to say that this is path connected. In other words, you know, you can every single point of this is connected with every single point, you know, of this region is connected with every other, you know, point of the same region, okay, through some path. So therefore you call it's a path connected region. Okay. And you call such a set as convex. Okay. So convexity is like a more stronger condition. So path connectedness is a weaker condition. So you're going to say that a subset of Rn is convex if you can join any 2 points of the region, okay, but by a straight line. And that line segment, actually, straight line segment actually, but that line segment should be entirely contained within that region. Now I can see, I mean, keeping it with this picture, I can immediately see that this is path connected but not convex actually. Okay, so can you tell me 2 tricky points actually? So if I take this point and try to join them through a line, so I'm not allowed to take a curve, then that line is not going to be, you know, entirely set in the curve. So what would be the obvious example of a convex set? What do you think?
Circle.
So a circle could be the example. You don't have to, you know, be Einstein to figure this out. You can really see the definition. Okay? So, you know, let me just write the definition properly. Okay? You've understood it's fine. Let me just quickly say that for a subset D of Rn is path connected. Okay? Is path connected. Okay. If you take any 2 points from the region, okay, you can find a path P, okay, in D such that, okay, such that P from A to B into D is a continuous map. You should have a path that is continuous, okay, with that satisfies this, that P of A is, say, call this A star and B star. If this A star and B is B star. Okay? So you have a region, you take 2 points, you can find a path that is continuous and which lies on, basically, that's what you're saying. So such kind of a region is going to be called the path connected region actually. Okay? And which set is not going to be path connected? I mean, can you think of something that is not path connected?